Hi everybody. So one of the things we've mentioned several times throughout this course is that these types of problems, these sample problems that we're giving you, are really to illustrate a concept. You're not going to see these particular problems once you get out in the real world. Why would your boss pay you to solve something that's already been done? So just memorizing solutions, well, I've got this type of problem, this is how I approach it, isn't very helpful. Instead, what we want you to do is to focus on these techniques that we're teaching you that can then apply to any kind of situation you run into. That's what's going to make you good at your job, and that's what's going to make you keep your job. So we've talked about gravity before. We've talked about how we get gravitational potential energy when I lift something up, because that energy is stored in the object because I've done work against gravity. And from that we derived the weight, which was just the mass times the acceleration due to gravity. So that weight is obviously the force due to gravity. But how can we prove that? So what we're going to learn this time is we're going to teach a technique for using the work, the expression for work, our definition for work, for how we can derive the definition of a force directly from that. And we're going to use this technique later on when we start talking about springs or any other kind of energy, or force that I'm going to be working with. All right, let's get started. Okay, so as we said, we're going to come up with a way to get the force of gravity from the work done by gravity and from the gravitational potential energy. Because remember, when I pick up my pen, I'm storing energy in that pen because I'm doing work against gravity. My arm is doing work against gravity. And so that work that I do against gravity is where that stored potential energy is coming from. I can't just create it out of nothing. Okay, so given that then, we know that the gravitational potential energy is equal to the work that I do against gravity. And I'm going to put that little g there just to remind myself that all I'm considering here is gravity. Okay, well, we know from our definition, our integral definition of work is going to be the force, and again, I'm going to put that g here just to remind myself that I'm talking about the force due to gravity, dotted into this differential dx, which is a vector. All right, so we know that then this is going to be mgh because we've got our definition for that. So that h is the height that I've gone. So let's say I've got my pen here and I'm picking it up and I'm bringing it up to this height up here, and that's going to be h from there to there. Okay. Well, in order to take this integral, I've got to get rid of these vectors. I've got to go ahead and take that scalar product. With what we know so far, we can't do an integral of a vector. So we'll just make that the scalar magnitude. So these are no longer vectors. Anytime that you are working with energy, you're going to lose all sense of vectorness. So you're not going to have any kind of a direction with it. They're strictly going to be scalars. That doesn't mean that the velocity or even the force in this case doesn't have a direction, because in fact it does. But it means that you, the physicist, you, the engineer, have to put in that direction afterwards. The math is not going to tell you that. So that's one of the big differences between doing a math word problem and doing a problem like this in physics. All right, so my definition, remember A dot B, so the scalar product of A and B is their scalar magnitudes times the cosine of the angle in between them. Well, we've already established that I'm moving straight up and my force is also in that direction. So the angle between them is going to be 0. And you may say, well, what about the minus signs? Well, remember, they're not vectors anymore. So this then I can take. Now, the force, let me just recopy what we have here so that we can see it. That's going to be integral f dx, where these are no longer vectors. Now, the gravitational force is not actually constant. Remember that the further away from the floor I get, the further away from the planet I get, then the less the gravitational force is going to be. So it actually does depend upon how far away I am. It's not constant. However, by the time I get up to the height of the International Space Station, well, I'm only at, say, roughly 90% of the force of gravity that I would have here on the Earth. So from the height of your ceiling to your floor, you literally cannot measure that difference. And as engineers, if it can't measure it, it doesn't exist. So we're not really making any mistakes here by assuming that the force of gravity is constant, as long as I stay within my room, right? So I can pull that outside, and so that gives me f of g is the integral of dx. Well, the integral of the differential is just going to be the variable itself, so that's going to be x, and I'm going to go from 0 up to my height h. So bringing it over here so that you can see what we're doing, we're going to have mgh is equal to the force due to gravity times, remember we take this first one, it's h, and then we subtract out the second endpoint, which is 0. And so I get this. And then finally my h's cancel. And so my final definition then, my mathematical definition, that's going to be a g, not an h. My final mathematical definition then for the force of gravity is this. And that of course is exactly what we derived, and we called it a weight, because that's what weight is. Weight is nothing more than the force due to gravity. They mean exactly the same thing. Okay. Now yes, we knew this to start with. However, now we've learned a technique for how we can derive a force from any kind of energy. If I know the work that that force is doing, then I know that there's energy being stored, because work is the exchange medium for energy. So it's an important technique, and it's one that you can apply to a wide variety of situations for that. All right, so anytime that we come up with a new expression, this f of g, this force due to gravity is mg, we've never really talked about it as a force. We've just said that it's the weight, and they are the same thing, of course. So what we want to do is we want to apply this to a situation that we've already solved before. Mathematically then, I should get exactly the same formula. Exactly the final mathematical expression should be the same whether I do it the old way or I do it the new way. If there's not, something's wrong. So this is the next technique that we want you to learn. You always, anytime you come up with something new, you want to confirm it with something that you found before for the same situation. So take a look on the next page then. All right, so we're going to drop, if you remember, we've done this problem before where we are going to drop a rock onto our hapless BattleBot enemy here. So we're going to drop that rock here onto the other BattleBot right here, with hopes of destroying it. So we want to know, we want to find the final velocity. And if you want to be really cruel, it's actually the impact velocity, right? That's the velocity at which it's going to hit that BattleBot. We want it to be high enough to destroy him. So for this one, we want to use conservation of energy. That's what we did before. We're strictly going to use conservation of energy. I'm not needing a time, I'm not needing an acceleration or anything like that, so I don't actually need to use kinematics. I don't have to for any reason. I can just go straight to conservation of energy, and conservation of energy is going to be the fastest way. What I'd like you to do is pause the video and work out this entire problem. Try to do it without looking back at your notes, because we have solved this. You have everything there. If you get lost, sure, go back and take another look at it, but try to see if you can do this without looking back. Pause the video and do this now. All right, have you got it? If you got stuck, did you go back to the previous parts that you have? If so, that's fine. All right, so let's do this the way we have normally done it. We're going to define our quantities. So we're going to define h to be the height in meters. My lowercase is even worse than my uppercase. And m is going to be the mass in kilograms. And then finally v is going to be my impact velocity. And that's the one that we don't know what it is. So that's our double question marks. Notice that the height and the mass we're assuming is given to us, even though I don't have a number, because I'm coming up with a general expression. So these would be knowns. Those would be things that you would find, that you would be given based on your experiment or whatever. The double question marks are indicating what you actually want to solve for. It's actually what you want to find in this case. All right, so even though there's no numbers, don't panic about that. We're just going to leave our h, we're going to leave our m, and we're going to assume that those are something that we actually already have a number for. But by not putting in the actual number, now we've got something general. All right, flip over to the next page then. So for our equations then, we said, when we looked at step 2, we said we were going to use conservation of energy. So always write down every type of energy that could possibly be in the problem. So we've got spring energy, conceivably, we've got gravitational potential energy, we've got kinetic energy. And then anything I have on the initial side, I also have to have on the final side. Now you may say, Dr. K, I don't have a spring. Why am I putting that in there? And if you recognize that, that's fine. But what we want to try to do is we want to try to take out as much of the forethinking that you have to do. Instead, we want to focus on one small part of the problem at a time. That way these complex problems become a lot more easier because you're just focusing on this one piece. So if we know that we always start by writing down every kind of energy we can think of, hey, we're good to go. But now we'll go back. Remember, in step 4, the only math you can do is mark out things that are 0 or things that cancel out. So I certainly don't have a spring. So my line there with a 0 means that it is actually 0. It's not canceling out. All right. Initially, so let's put our picture back here so that we can see what we're talking about. So my ball starts here. My robot's over here. And then it drops down here and hits the enemy robot. So what is the initial velocity? It's 0, right? Because I'm getting ready to drop it. Do I have kinetic energy, or do I have gravitational potential energy? Well, sure, right? I'm up here on the wall, so I definitely have some gravitational potential energy. Now, when this thing hits, we've already decided there's no spring energy. Is there any gravitational potential energy? You need to be very careful, as you may have realized last time, is you've got to set your 0 somewhere. Right? So we're going to set our 0 right where this thing makes impact. So just so that I know what this H is. At the bottom of that H, I'm going to make that my 0. You can do it anywhere you want, but you got to keep up with it. So if that's true, then do I have any gravitational potential energy? No, that's also 0. So I'm left with UGI is equal to EKF. Well, these are unknown symbols. I know you know what they are, but if we were going to be really technical about it, in my step 3, I would need to add these as unknowns. So right now my unknowns are the impact velocity, and that is in fact a vector, my initial spring potential energy, that's going to be in joules, and my kinetic energy final, which is also going to be in joules. Okay, so that would mean that I would need 2 more equations. Well, we know what those equations are, right? My gravitational potential energy, I'll just go ahead and write it down here. My gravitational potential energy is going to equal mgh, since that's where I'm sitting. And then my EK, my final kinetic energy, is simply 1/2 mv squared, where v is going to be my impact velocity. All right, so I've got 3 equations, 3 unknowns. Did you get this far? Now, if it's okay if you went straight to saying mgh is equal to 1/2 mv squared. And hopefully, eventually you will become comfortable with that. The only reason why I'm writing them out separately is back to that idea of just focusing on one piece at a time. While you're learning, that's a good idea. Eventually, you might start to combine some of these steps, but when you do, you got to be careful. You've got to make sure you're still thinking mentally about all the combinations. Because as we've seen before, you can sometimes get a pretty dramatically wrong answer if you just assume something and keep going on. All right, so we're ready to solve the problem. So I'm going to go ahead and start with this equation right here. So I've got UGI equals EKF, and then as we saw over here, that just means that MGH is equal to 1/2 mv squared. My m's cancel. I'm looking for the velocity, so I'm going to solve for that. So I get 2gh is equal to v squared, and so v then must be equal to the square root of 2gh. Now that's a scalar magnitude. If I want the velocity, if I want the vector velocity, I need to establish a coordinate system. G, of course, G is also a scalar magnitude as well, because there is no vector, there are no sense of vectors here when I start talking about energy. So that's also a scalar magnitude. So don't think that, oh, well, that's going to be a negative 9.81 and I have to keep up with all this. No, it's just 9.81. It's a scalar. So if we defined, for example, down to be positive, then my velocity is obviously in the positive direction. Remember, anytime I take the square root, there's going to be a positive and a negative root. On the other hand, if you defined up to be positive, now what's my velocity going to be? Now it's going to be negative. So the point is that it depends on you what that sign is, not on what the physics says. There's not a physical reality that's going to tell you whether it's positive or negative. You decided that when you establish your coordinate system. Okay, so we've done this before. hopefully you were able to do it without looking back at your notes, but all of this is straight out of what we've done before. Okay, so our next step then is to use our new technique and see if we get the same answer. All right, so we're going to go over here, we're going to do the same thing, and we want to find the impact velocity again. But this time we're going to use the net force. So my plan though, since I want to use the net force, well, okay, I need to know the impact velocity. If I have a constant force, I must also have a constant acceleration. So if this is g, my force due to gravity, is g constant? The answer is no, it's actually not, which would mean then that my acceleration, since g is my acceleration, is also not constant. So technically I can't use kinematics, can I? Because you can only use kinematics when my acceleration is constant. However, remember that we said that from the ceiling to the floor, I'm not really making any mistake by assuming that it is constant, because you simply cannot detect the change in it out to 8 significant digits or whatever it is that you would need to be able to do that. So we're okay saying that this g is constant, and that means this force is constant as well. Well, as we said, anytime you have a constant acceleration, your brain would scream, use kinematics. But kinematics requires that acceleration. So that means that I'm going to use the force then. So I will use the force to get my acceleration, which in this case you should be able to see is just going to be g. However, if we weren't sure of that, remember that it's F equals ma if and only if what? If that mass is constant. You cannot use this shortcut if I'm dropping this thing on and it's shedding mass as it comes down. That's simply not going to work. But also means I won't have a constant acceleration, and so I wouldn't be using kinematics for that. Okay, so even though we know already that this is my ma and that g is going to be my a, right? We're learning the technique. We're applying what we have here so that we could apply it to a case where I didn't know what the acceleration is going to be. Because lots of times I don't know what the acceleration is. My robot's just moving and it's got some acceleration. Okay, so then we will use kinematics to find the impact velocity. And that's going to be under a constant acceleration. That's what we're going to assume. And again, that's not true, but it's close enough. It's for what we're doing here, we're dropping that robot. Now, if we were dropping a rock from the space station onto the Earth, then that's definitely not true. I'm definitely not going to be able to assume a constant acceleration. All right, so defining our quantities again, we have, whoops, I don't want that. I want h. So I'm going to have h is going to be my height in meters. And that's going to be given to me, right? And I know that my mass, m, is going to be my mass in kilograms. Now, if we're going to be thinking about kinematics, we know we're going to have some other variables, but let's go ahead and keep the same symbols that we know so far. So this is going to be my impact velocity. Let's don't call it F because we could get confused with that. So we're going to call that our impact velocity. And that's what we want to solve for. Okay. All right. I want you to go ahead and go over to your next page, and then that way you've got that room to fill in. If I do that here, then I'm going to lose all the notes that we've made. So I am going to stay on this page as we're going through it. All right. Give myself some room to write here. And then I'm going to go ahead and draw my picture here just because, to make sure that we all are on the same page as to what it is that we're doing. And so this is the mass of my projectile, and this is my height, and then it hits with some impact velocity. Okay? All right. So we've already said that we're going to use the net force. Well, the reason I want to use the net force is because I want to get that acceleration. So I have to have my constant acceleration before I can even start kinematics. There's no reason to do kinematics unless you have that constant acceleration. So we know then, if we're looking at our step 4, we know, of course, that we're going to have our new formula, our new mathematical expression. And that's going to be f of g. Now this is a vector, so I'm going to have to be really careful about my directions. Let's make this positive again. The reason I like that is because g is now in the positive direction as well. Okay, so we've got that because we're not going to use energy. So now I've got vectors. Okay, so we're going to use that to find the force, and then we're going to use this to get our acceleration. Well, that's obviously just from Newton's second law. The sum of our forces, and there's only one, is going to equal my mass times acceleration. So that's technically what we're doing here. It's trivial, it's easy, there's only one force. You can totally get that. But let's write it down to make sure that we're keeping up with that. All right, and then I know, according to my goal here, I'm going to use kinematics. So we've talked about the net force. We've used the force to get the acceleration using Newton's second law. And so now I'm going to use kinematics. Now, which kinematics equation do you think you want to use? Well, I want a velocity, and I've got a distance. I've got a position. So I probably want to use velocity versus position. So again, I want to keep my symbols. I don't want to just use those F's and I's. I'll put the I here, but we know that we started out with 0. Plus 2 times my acceleration times my delta x. Okay, so I've added a new symbol in here. So I now know that delta x is going to equal my displacement, my change in position. Let's just call it the change in position. So that's my change in position in meters. And let's go ahead and record our other symbols that we have here. We have f of g is the force due to gravity, or the gravitational force. And we don't actually know what that is, but we know it's in newtons. I know that A is my acceleration. And I don't know what that is, but I know that it's in meters per second squared. All right, so taking a look here, have I added any new ones? Right, so right now I've got 3 equations, 3 unknowns. I'm good to go. The physics is done. There's nothing now to do but the algebra. All right, so let's start with this, with the kinematics equations. That's going to give us what we want. I'm not going to take the square root until I've got everything else plugged in. So that we know is equal to 2ax. Now, technically these are dot products, and my acceleration has to be in the same direction. So when I take that dot product, then the vectorness of this goes away. All right, so that actually should be a dot product because I can't just multiply 2 vectors here. But the acceleration is definitely in the direction of my delta x, so I'm okay. All right, so now I need to substitute in for delta x. Well, delta x in this case is going to be from h to 0. All right, so delta x then we know is just going to be 2a. It's got to be an h because it's actually h minus 0. Remember that I don't have any sense of vectors, but as I go from h to 0 here, I'm actually moving in the positive direction. So I'm going to leave that as an h. All right, so we need this acceleration. So we've used this one. We're done. We're going to use this one here. So even though this one is rather trivial, there's only one force in the problem, and that, of course, is gravity. And that's going to equal ma. And so f of g over m is going to equal a. So let's put that in here. So v impact squared is going to be 2 f of g over m times h. But I know, so I've used this one, so now I have my last one here. I need to plug in for my f of g, and I've got v impact squared is equal to 2mg over m times h. Those cancel, and we're going to get something that looks very familiar. I take the square root, take the square root of both sides, and I get 2gh, which is exactly what we got before. So solving the problem this way then, allows us to be sure that our definition actually works. And so this technique of taking an energy and then using the definition of work will allow us in any situation to figure out what force is actually putting that energy in there, what force is doing the work from that. And that's the new part. That's the new part. So if I know the force that's doing the work, I can get that from the energy and I'm ready to go. So as you're going through your homework, keep these things in mind. I mean, what we've done here, we've solved the same problem twice, right? And so that's not terribly difficult, but the concept that we're doing actually matters, how we're doing it. We're learning it on something easy, something that we already know, so that we can apply it to something that's new and maybe a bit more complex. So now we have another technique in our arsenal, this idea of being able to get a force out of the energy, because most of the time we are going to know the energy, or at least have some way of kind of figuring out where that energy is taking place. However, we also will sometimes simply know the force. I may have a rocket engine that's applying some sort of a force. I may not offhand know how much energy I'm getting out of that, but now I can use the force to get that energy. Because as that force is applied over distance, well, that's work. And that's how much energy that I'm putting into the system. So it goes both ways. So keeping this technique in mind, even though we derived it for something simple like the gravitational force, keeping that technique in mind is going to make you have a whole lot more options as you come to try to solve a problem. We'll see you next time.